I can just ask these guys, and if unless they have a problem. Okay, 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 okay. Sounds good.
Okay, so welcome back to the post-tea session, the pre-lunch session. Now we will have the second talk from Professor Amitabh Nandi. I think this one will be more of a pedagogical talk, if I'm not mistaken. Yes, please go ahead.
Thank you, Shakti. Can you hear me? Like, am I audible? Yeah. So I must say I'm not really prepared for this pedagogical talk. I had some ideas, but then I thought that because all of you come from such diverse background, so I thought like I should start with something very simple, and then like we see where it goes. So the main idea was, so the initial idea was, as you can see, I wanted to discuss how, like, what we look at is really like the physical mechanisms in an experiment and try to develop a model. So the question is like, what kind of tools from physics you can use or to quantify the data, to quantify experimental data, so that you develop some insight about what is happening. Because sometimes just staring at the experimental data where things are moving around, yeah, I'm particularly talking about experiments where you are seeing a lot of dynamics and movement or structure. So, but sometimes just staring at it, because of the fluctuation or noise, you cannot say something immediately. So what kind of quantification one should do to develop some insight? And I wanted to talk about that. So the main idea was, I'm talking particularly about like one kind of data. It is like coming from really microscopy experiments where you have spatiotemporal information. For example, you are looking inside a cell, you are seeing proteins moving around, like nutrients moving around, and you can track a single particle over time, record, like write down the position versus time, and you basically have a trajectory in 2D or 3D or even 1D, depends on what kind of experiment you have. And so it has this information, so you are looking at a single trajectory, or if you are looking at, particularly in the context of morphogenesis, if you are looking at lot of these particles, like cells moving around, okay, so they are interacting with each other, cells moving around, forming some structure. So you can see there is some formation of structure, but the scenarios when the structure is not immediately apparent. What kind of things you can tell about by quantifying the data? So there, this data is something like spatiotemporal data. So I have for some reason removed the spatiotemporal term. So because you have many individual entities in space and they are all moving around interacting with each other. And the main idea always ends up with that we extract some information from the data, and based on that information, we try to build up a model, okay, and see that if we can explain certain things about the system which we are trying to understand, but that does not end here, because writing a model, it might be one of those models. What you need to do is, your model can have some prediction, but then you need to go back to the experiment and say that, hey, my model had these parameters and it is predicting this. Now, what is the meaning of those parameters in the experiment? Can't the experimentalist switch off one of these parameters or tinker around with this and see if they get some behavior which is still explained by your model? So there is a little back and forth between the model and this experiment. So this is one part, and then you also want to see that you are looking at some general phenomena and you don't want 10,000 different models where for each system you have a different model. You also want to identify some underlying principle which you can take out, and that might hold true for similar scenarios in the experiment, say for a different organism. So broadly, this is the overall idea. And what I wanted to start with is a very simple thing. And as I said, like maybe I will not be able to reach the end, so that's okay. So I think during this talk, like during this workshop, one thing which has been focused a lot is the phenomena of diffusion, right? So there were several talks on reaction diffusion system. So I just wanted to quickly touch upon this idea of the microscopic origin of diffusion. So probably all of you know. So if you think of diffusion, so the way you think of diffusion in this deterministic dynamical systems is you have some concentration of some protein molecules and they are spreading. They are spreading and you associate some number D with that. So there is some kind of a symmetric spread. But the microscopic origin of this kind of diffusion is, you can go back to this original experiment of a pollen put in a fluid, and what happens is this fluid is in equilibrium at a temperature T, and it is, the fluid molecules gets the energy from whatever is the ambient temperature, and when you put the pollen, this bead which is here shown in yellow color, it gets kicked by the fluid molecules and it does some kind of a random walk, okay. So in a sense that at every time the kick it is getting is completely uncorrelated. Now there are several models to really study this, and again I will show some equations, but you need not worry about the equations. Probably some of you don't know, some of you know. So one can write down the equation of motion such a particle which is getting energy kicks from the background fluid molecule, and the equation kind of looks like this. I will quickly explain what it means. So if you think of a fluid which is very dense, which is highly viscous, then you can, so this is basically the drag, the viscous drag, because every time, so this is basically, this comes from frictional forces, because every time it tries to move in some direction, it is feeling some drag forces because of the background fluid. And the second term is the drag, and the first term is simply the Newton's term, it's mass times acceleration. But typically if you have put this in a very viscous fluid, which is typically the case for the fluid inside a cell, or in most of these biological scenarios, fluids are highly viscous, so you can practically drop this term and you can rewrite this equation in this form, and So what is this equation? This is the same equation rewritten in this form where the constant has been redefined, and there are valid reasons to write this constant in this way, and this d is the diffusion coefficient, and I will explain you in a different way. So what it means is this psi t is the corresponds to the kicks this bead is getting from the fluid molecules, which are uncorrelated, and that property that the kick at different times are completely uncorrelated is given by this condition, that if you take this psi at some time t, this kick, this psi at some different time t prime, they will be 0 if t is not equal to t prime. Okay, so that is basically what is known as a delta function correlation. Now there are various things associated with this, and if you were asked to say, I think of this simple, so this bead is diffusing in 2D. Every time you can, as an experimentalist, you can record the x, y position at different times. If I think a simplified picture, say it is just a one-dimensional process where you have a line, you have this bead. I'm going to a simpler version of this. It can either move to the left or to the right. Okay, so, and this moving either to the left or to the right is completely random. So there is some probability associated with it. So if you can work out this problem, this is equivalent to what I have written. So this is for a single particle. Now, yeah, I will skip this, what I have written here for the moment, and I will come to this later. That is the most important thing. Now, if you think that you are not looking at a single particle, a lot of particles, like some chemical, and this is what you had been studying. So in that case, instead of writing down the equation of motion of a single particle, I would rather think in terms of a concentration field or a density field for these particles, and the time evolution equation for such a field is given by this. This equation you have seen before. Is that correct or no? This equation everybody has seen, right? This is the diffusion equation. This d is the diffusion coefficient, and I am claiming you can systematically start from this equation and derive this equation. Okay. So, and now you recall when you were studying these reaction diffusion systems, you had this term. Additionally, you had some chemical process also to tell you like how this concentration will evolve for these different chemicals. But here I am talking about, so the difference was there were chemicals which were diffusing. So here this P, you are starting with something like you had a particle, and now you want to ask that from here. So let me go a little slow. So because this is a uncertain process in a sense that at every time this particle is getting random kicks, as an experimentalist, when you write down these different positions, say x1 at time t1, x2 at time t2, x3 at time t3, and so on, say you knew what was x at time t equals to 0, right? That you have absolute control as an experimentalist. So if this was a deterministic dynamical system, given this was known, you can find x at any time t because this follows an equation right? But what this equation you don't know. The evolution of this system is probabilistic, is stochastic. So you cannot write down such an equation. So in that case, what will you do? Then you cannot write this equation. What you can ask is, you can ask that what is the probability, I know these values, what is the probability that at some time t1, the position was x1. At some time t2, the position was t2, and so on. So if you have any questions, please stop me and like. Okay. Now, you can see that this is a incredibly difficult problem for a given system to exactly find out what will be the probability. So there are several simplifications, and simplifications based on observation. So one simplification which everybody works with is the fact that, okay, so here when I write this, so you can think that t1 is the latest time. So t1 is greater than t2, greater than t3, greater than t. So tn was the earliest time. Okay, so this is the way I have started. Here, I think, yeah, this should have been reverse. So let's say, let me change so that there is no confusion. So the current time is, say, t1. Okay. So now it is very difficult to compute such kind of a probability, and I mean, people had worked on this theory of probabilities, and now you are looking at a time-dependent probability, evolution of a probability. So one simplification is, you say that it depends only on the current, whatever is the position at the current time. It does not depend on the history, and that is known as a Markov assumption. So typically for a Markov process, so if it is gone from here to there, I have gone from here to here, so my step coming over here only depends on where I was in the previous step. So then what you can do is you can simplify, say you had this, so you can write down, say, some intermediate time tr, and you want to know what is the probability that you have reached here. So then it would mean that you can truncate this you don't need to know the earlier times. If you want to know the probability until this, knowing what was the position at r plus 1 is sufficient. And of course, now you can start simplifying this. I will not go into the details. You can use something called Bayes' theorem, where just I'm flashing this idea. You can discuss with me later, because I want to get into other things. That if you want to know like some probability at some time t1, and so this you can write down as the probability x1 t1 conditional on x2 t2 times the probability of having this position x2 at time t2. By the way, I am using the same notation for these probabilities. These are different probabilities for each of these. Okay, in principle, you can use different notations. So using this, you can write down, and again, I will not go into the derivation. One can write down a differential equation for the time evolution of the probability. So this is very important, because then that will tell you how this system probabilistically evolves over time. And let us look at a simpler version of this example, and I will, at least this example I will work out, and you can see that why it works. So let us think of I have a discrete line. I know the positions. So say it starts from some minus infinity, say. Now this is the position 1, this is 2, this is n minus 1, this is n, this is n plus 1. Now suppose I have a particle similar to this particle. Currently at the position n. Now the particle can hop to the right or hop to the left with some probability. Let's say it hops to the right with some probability p, it hops to the left with some probability q. Okay? So if I ask you, what is the probability that the particle is at a position n at time t plus delta t? So what is the probability? So I have to count all the possible ways that it can end up at n at time t plus delta t. So what are the different ways? It was at site n minus 1 at the previous time, and with probability p it hopped and got here. So I should write p, small p times p n minus 1 t. It could have been at n plus 1, and with a probability q it hopped and got to n. Anything else? The fact that it stayed at that site, so that should depend on the condition, because these are probabilities. If p plus q is less than 1, then I should also have a probability that it didn't move anywhere. Right? If it was 1, then it is 0. So it depends, but in general I should write it. Right? Now we are looking at really like small increments, so one can do Taylor expansion. So one can see it will give us so I can cancel these two terms. Now I can take this delta t and divide the right hand side. Okay. So if I do that, these quantities are no more probabilities, these are rates. There were transition probabilities, now I can call them transition rates. Okay, so I will redefine them. And so on. So sorry? Thank you. Yeah. So now you can see I have got an equation . So if I say that I will now assign some dimension, these are not discrete points, I will assign some space dimension to this. Okay, I assign some delta x, and I will go to the limit where I have these delta x's are small. Basically, these particles are continuously moving. So what I can do is, I can go from this definition, I can write x equals to some n delta x, and go from n to the x definition. So now, instead of discrete hopping, I am looking at continuous movement. So clearly, I should write it as p of xt. Secondly, let us make another assumption. Suppose initially this p tilde was not equal to q tilde, which means the rate at which I hop on the right is not equal to the rate at which I hop to the left. Okay, but now if I make it equal, that the transition rates on both sides are equal, so I will call it some p naught. So this equation then simplifies a lot, and you can tell me what is this equation. So now I have to consider the limit of delta x tending to 0, because I want the space to become continuous, and this becomes dpx dt. What is this one? So I can write down p naught, and this is x minus delta x. So if you Taylor expand this quantity, p of x minus delta x, what will you get? You will get px minus delta x p prime x, or maybe I should now, because I have two variables, del p del x. Similarly, for p x plus delta x, because I will get an x plus delta x from this term, I will have p of x plus delta x del p del x. So now there is a problem, right? What is the problem? The problem is the following, that the moment I express this one as px minus delta x, this thing, and px plus delta x as px plus this thing, these two terms will cancel. So I have to retain another higher order term, which is and that is always positive, irrespective of, and of course we have this minus 2p0 p of xt. If I put all this in this equation, can you tell me what will we get in leading order? Oh, sorry, I made a mistake. Did I make a mistake? No, it is fine, right? Yeah. So what is there in leading order? This px and this px, there is a 2 p naught px t. There is this minus 2 p naught px t, and plus half delta x square del square p del x square. Am I correct? So this is, sorry, this board work is getting a little messy, but are you okay with it? So what did I get? It is a p naught here. So what I got is simply, again, I have to be careful because I have two variables. Now, I should take partial derivatives. So, what I have got here is now what is this quantity? This is a hopping rate times a length scale, which is delta x square. So, I can call this as something like a diffusion coefficient. So, what you have got here is simply this equation starting from a simple discrete process which can hop either to the left or to the right, but with equal probabilities. So, these are all equivalent. Okay. So, this is basically the origin of what we know as diffusion, that it is a complete random walk at the microscopic level which gives rise to this kind of a diffusion equation. If the P and Q were different, you had a higher probability to jump in one direction compared to the other, you have to, in that case, define two variables. One is a P minus Q, say P was greater than Q, which is say V, and P plus Q by 2, which is D, then this system will be like an advection diffusion equation, that you are diffusing, but at the same time you have a bias to move in one direction with a higher probability. Okay. So, now with this definition, so we understand that this system is basically nothing but like a random walker at microscopic scale. Now, if you have such a random walker, which you see in the experiment, which looking at the particle, you cannot immediately understand that it is a random walker because this is just mathematical equations. You are not able to verify these mathematical equations. So, there must be some way, just by looking at the trajectory, you can say that whether it is a purely random walker or not. And that identification is this quantity. This is something you can measure from experiment. What is this quantity? And this is the quantity I will spend some time. Are there any questions? So, can I remove this or? So, when you see something like this bead moving in a fluid, you can take the trajectory and let me. So, what happens inside the cell? Inside the cell, this bead is not freely diffusing. What it can do, it can bind to the molecular motors and move in a directed fashion along these tracks which are called microtubules. And when they are moving along these microtubules, they are moving with some velocity, some constant velocity. Okay. Now, if they unbind from this microtubule, then they are in the bulk cytoplasm and then they can diffuse. So, your actual process is, so this is very crucial, that any kind of transport inside cell, it is not only diffusion or not only like a moving with a constant velocity. You need both. Why you need both? Suppose you want to reach the target which is at that end. If you had a constant speed, but your direction was different, you will walk in this direction and you will completely miss that spot. So, moving with a constant speed helps you to traverse large distances, but diffusion helps you to find the right direction because you are constantly changing direction. And if you were only diffusing, then you have not moved much because you are far away from the target. So it is the combination of these two which gives you the, like, reduces the time and makes an optical search strategy for whatever reasons, like for whatever experimental scenarios you look at. So now, if you have, you have a trajectory where from the experiment, you saw under the microscope something like this, you have recorded X and Y and T. You have n data points. So how can you characterize that what kind of motion it was? So it can be characterized through this exponent. So what you can do, you can calculate this quantity from your experimental data. So how do you do that? And that is what I'm going to spend some time, but let me first let you see this equation carefully. So this is a very important equation, particularly if you want to quantify the nature of the motion from experimental data. So if you can calculate this quantity on the left-hand side, which is the mean squared displacement, which I'm going to explain soon, it has this following time dependence. It depends on time to the power some exponent alpha. And this alpha will tell you what is the nature of the motion. So if alpha equals to 1, you get from experiments by fitting the experimental data, then you are sure that this was free diffusion. If alpha equals to 2, you can already see this. Moving with a constant speed, if you calculate x is Vt, I have dropped the constant, then x square is V square T square. So the mean square displacement, which is the square of the displacement, depends on square of time if you are moving with constant speed. If it is diffusion, it is 1. If it is a combination of diffusion, if it is not diffusion, but you have lot of crowding, you are not able to freely diffuse. Every time you try to diffuse, you bump on an obstacle and your motion gets reduced, then this exponent will be less than 1. Sorry. Yeah. And now you can see that if you had a combination of various kinds of motion, your exponent can be between different values, which you can try to, like computing this, you can try to infer. So this is a typical mean square displacement plot for some simulation data, but you can do the same thing for experiments. So how much time do I have left? I think I spent too much of time in this thing, but about 20 minutes. So how do you compute this quantity? So what you do is the following. So here I'm going to again maybe spend 5 minutes. Put the full thing. I will switch some of these topics. So the way you calculate is the following. Suppose you had, I will show you for a one-dimensional trajectory. Suppose you recorded the position, only one position, the x position, as a function of time. So this is some trajectory as a function of time. And you know the different values at different times, T1, T2, T3, T4, and so on. So what you do, you exactly use this formula except for those L. The L's are if you have higher dimensional data. So basically, you set, say, you take the difference between these neighboring data points. You calculate x at t plus delta t minus x at t and take a square. Now you take the successive differences, you take the next 2 points. So you took the difference between 2 and 1 and squared, and now you take the difference between 3 and 2 square, 4 and 3, and in this way you keep on summing. And then you divide it by the number of pairs. Okay. And here you plot, so your gap was 1, so I put a index which is k for gap 1. I got a single number by summing the square of all these differences, and I put it here. Now in the next instant, I increase the gap. I had 1, 2, 3. I look at the difference between 3 and 1. And again 4 and 2, 5 and 3, and so on. And then again do the same thing. So now you are looking at x at t plus 2 delta t minus x at t whole square plus x at t plus 3 delta t minus x at t plus delta t whole square, and so on. So you will get a number over here for k equals to 2. And in this way, you keep on increasing the k, but the problem is, as you increase the k, you are increasing the gap between these points. You are not considering the intermediate points, but because the number of pairs are also reducing. So you cannot go to very long, so soon you will like see lot of fluctuations here. So now, nevertheless, when you have these points, you fit this point with the equation which I showed, this quantity alpha. And then whatever value of alpha you get, that will tell you what is the environment in which your particle is moving. Whether it is moving actively or it is doing a random walk. So, yeah. Any questions? Yeah.
Then we take between so then
Yes. So you can see from here. Just forget this this summation. If you look at this summation, you see I have a k. When you put k equals to 1, what is the different numbers? I goes from 1 to this. So the first number is k equals to 1, x2 minus 1 minus I is 1, x1 minus x0. Then the next term is x2 minus x1 plus x3 minus x1 all square. Now when you make k equals to 2, the first difference is, the first term is x2 and this is x0, right? So you are removing one point, you are looking at a larger gap. Now, there is another way to make this quantification if you can do the experiment repeatedly. So you follow this formula only when you can do the experiment once. You have a single time trajectory. If you were able to make this measurement repeatedly, starting from the same initial condition, then you could have done it in a different way, which is called the ensemble average. You are doing this averaging over a single time trajectory. So this is a crucial difference. Now, there has been some remarkable studies in this. So what I was telling you was to calculate this mean square displacement, a single value out of a single like whole trajectory. So this is a paper where what they did, they performed this mean square displacement over small windows. They took like a small box, calculated this whatever delta x square formula, and then they slide the window over this, and then they get a distribution of this exponent. And the distribution of the exponent already tells you like at whatever time, if there was a change in the nature of motion. So suppose it was stuck in some place and then suddenly it got actively moved. So all this information can actually come out from this kind of thing. I will, for the sake of time, I will not go into these details. I will quickly go into something which like is the theme of this now, I was talking about a single particle moving around. Suppose you have many cells, say. So these are the nuclei of the cells. And you want to infer about what gives rise to the spatial structure, how they are interacting with each other. Can one infer something by analyzing this data? And you can do various things. And one thing is, yeah, I skipped that. For example, you take the cell centers, and so those who use MATLAB can actually do that. So you take the cell centers and make a triangular mesh of this network. It is called Delaunay triangulation. Okay. Now what you can do, for this triangulated network, you can calculate the velocity gradients at the center of each triangle, and then you can use some like these are already inbuilt in MATLAB, so you can actually map back that gradient values at the vertices. Okay, so what is the point? If you know the velocity gradient, if there is collective flow of these cells, you can calculate something like if there is any vorticity in the movement. So you can calculate the curl. If there is some kind of an expansion, you can calculate the divergence. All these things you can do. So for example, this is an interesting thing. So in this case, so without going into the details, so what was happening here, so you have cells which are collectively moving and rolling in the third dimension. They are jumping, like doing swirls in the z direction. Okay. So now if you calculate the vorticity, the curl, what will be the direction of the curl? So it will be grad cross v. If this is circular, you will use the right hand rule. It will point in this direction, and actually we see such signatures. So these vectors here, sorry, it's very noisy, but they show this kind of a leftward direction, and there are some angles, and the reason is they are not exactly parallel. They are something like this. Like on both sides they are like this. So for the left half, you can use this angle which will be tilted in this. For the right half, it will be slightly there, but the major component will be on from the right to the left, and that's why you see this kind of thing. So this is a nice quantification because it was not immediately clear by looking at the swirling motion that because of too much of noise, but once you quantify an average over to suppress the noise, this pattern emerges out. Okay. So this is a very common thing which you want to quantify. Suppose you have some motion. Although by eye you can see that probably they are moving in one direction, but there are a lot of fluctuations. So how would you quantify what is the net directed motion? And what you can quantify is something called the polarization. So you take the individual velocities, sum over all the individual velocities divided by, basically you are averaging over the unit vectors in which they are pointing. Okay. So if they are exactly pointing in one direction, this quantity will be 1 because it is divided by the total number of particles over which you are summing. If they are all random, it will be 0. But sometimes this motion is not exactly binary, that 0 or 1, it can be somewhere in between. So as a result, this is a very simple estimation which you can do for experimental data. And so this one we calculated for the the problem which we are studying, and we found that like how this polarization drops as the cells move from one region to the other. But I'm not going into that details. So again the mean square displacement, which I have already discussed. What I wanted to discuss is something which is, this is the last one, which I would like you to understand. And this is a very useful quantity. So each particle or each cell or nutrients inside cells, say they are interacting with each other, they are moving in some direction. And you want to ask that how the speed of these individual particles are correlated with their neighboring speeds. So will the speed of this one particle is getting influenced by the presence of other particles. So if it is getting influenced, you will see some kind of a similarity in the movement of this particle with respect to neighbors. And you can think, I mean, the common thing will be, as you take a particle, the neighboring ones, because of interaction with them, they will probably try to move in some direction. If there is no interaction, they will be completely random, independent of each other. So basically, if I compute this quantity and plot it as a function of, so just ignore the plot which is shown below, just focus on this thing. So you are looking at, say, particles which are moving in various directions. So what you do here, so each particle has a speed u, I. I is the index of the particle, okay. So this is u1, this is u2 and so on. Now what you are doing, you are looking at how you take basically a point at the center of one such particle and draw a radius of r, and then take a small annulus of radius r plus dr. Whatever cells are there within that annulus r plus dr, you calculate this quantity with respect to this ith particle. So basically what you are doing, and you can vary this r. So initially you start with a very small r, you draw a small circle and then start increasing the r, the delta r being fixed. So what you are doing, if you plot this CR as a function of r, at r equals to 0, it is the correlation with itself. You are not looking at any neighboring particles, you are just there. You make a small radius, you are looking immediately at the neighboring particles. It can be that they are influencing the motion of this particle, so you get a high value. And as you move away, you are looking how far away particles are correlated with this particle. So typically what you will see is something like this, that as you go at large distances, this particle and particle here and particle here are not talking to each other, but particle here and particle here are like can talk to each other. Whether they talk to each other or not, or if they are like doing something else, would come out clearly once you calculate this quantity. Something which is not immediately apparent from the data. So yeah, so how much, so did I overshoot? I can take 2 more minutes and finish. So all these things I was talking about, where you have cells where you can exactly under the microscope track the individual cells. You can see where is the center of mass at a given time. But sometimes there are scenarios where you are not able to distinguish between two cells. The fluorescence is such, you see some kind of a mix of a fluorescence, but you see there is a dynamics of this fluorescence, they are moving. In that case, whatever I have discussed, you cannot do any of this. You cannot, because you cannot track these positions and calculate these velocities so cleanly. So that is a problem. In that case, what one should do, one can use something called a particle image velocimetry, or PIV. So what it does is, I will not go into the details. So here you see there are a lot of small nutrients which are moving around, right? look carefully, so this is actually inside a cell. Each of these green dots that are coming from the cell membrane are actually nutrients or vesicles carrying some protein, and they are coated with some protein which is the clathrin, which is shown in green. But there is also some static clathrin here which are not moving, but one should focus at all these dots which are moving from cell membrane more towards the internal side of this cell. And because you cannot distinguish each of these track, sometimes you see them, suddenly they are lost, suddenly they pop up, and two of them are fused, so you cannot do a single particle tracking in this case. So in that case, what you can do something called the particle image velocimetry. The short form is PIV. You can look up. So the main idea in PIV is the following. So you take this movie and you bin the movie. You make like squares. And in each bin, you keep a count of what is the intensity at a given time. And in the next instant, you again map that bin, that grid on the movie and see if there was a change in the intensity in that box. And you calculate the correlation between these two times, and from there you calculate an effective speed. You give a directionality over each bin. And in this case, there were a lot of corrections that was made to the movie, this drift correction, because there was some kind of a adjustment and intensity correction. But what you
What is this drift? Is it a background drift of the medium?
I cannot hear you.
The drift, is it the background drift of the medium?
This one.
So yeah, drift correction. What
the drift
drift
correction is, see, I think there is like the setup, the table on which this was done. I don't know, for whatever reason, there is like an overall center of mass drift. And if we don't correct it, the speed values which we'll get will have that component, so which we don't want. So we removed that component and then did the PIV. So I don't know exactly what is the source of that drift, but it could be in the experimental setup itself.
But it has to be with the sort of background motion of the medium, right? I mean, if not, you would not need to correct for it.
No, this adjustment, I'm not sure. So this is, the cell should be completely static.
Right.
If the overall cell moves, that we don't want, because we want to estimate the flows inside the cell when the cell is static.
So one is correcting for that overall movement, I suppose.
We are correcting for that overall movement. Yes. Okay. So, but now I can show you how this PIV looks like. So we plot these vectors of this averaged over all time, and what you can see is a very nice collective flow from the cell membrane towards the inside. So here we were not able to track any of these cells, but we use this PIV analysis to get an insight about what is the collective motion. And you can see the symmetry in this flow. It has a polar symmetry. If I ignore for the moment these differences, like it is slightly elliptical, and assume that it is almost like a circular thing and everything is flowing from around, you can integrate over the whole polar angle and get the radial component of the speed. So for example, we can take this, integrate over all the theta and plot the radial speed. So you see, close to the membrane, it is a large negative number. Negative because it is moving from the membrane towards the inside. And as it comes close to the cell center, it starts slowing down. What you can do is you can also quantify the net directionality. So basically, we are looking at, since everybody is coming inside symmetrically from the outer membrane, radially inward, you can define an angle which is the angle of the velocity vector minus the polar angle of the position, and that will always point at pi. So if they were all moving in random directions, all possible directions, you will get like everybody is scattered. So yeah, I will stop here. So the bottom line was to give you an insight of, if you have spatiotemporal data, what are the things you can do, and more importantly, the fact that diffusion is ubiquitous, what is basically the origin of diffusion, and how one can quantify any kind of diffusional process from tracking data. So I can stop here. If you have further questions, please ask me, and we can discuss later also during lunch.
So any questions?
So you mentioned that the spatial correlation quantity is kind of a way to look at how neighboring cells, for example, influence
in a
the
correlated
movement. Yeah. So the quantity might be high. I can think of two scenarios where it can be high. For example, where the neighbors influence the movement of a particular cell, or in a case where there's some sort of a global cue which would make the cells move in a particular direction. So would there be a way to distinguish between two such movements?
Very good question. What you have said is absolutely correct, and I will give you an analogy. Suppose there is a global queue, like bunch of people, lot of people are going to attend some event, and you are on top of a like high-rise building. When you see them, you are seeing like the collective movement.
Yeah.
If you calculate this correlation, it will be masked by the overall movement. You cannot see how locally the velocity is influenced by the neighboring velocities, right? So in that case, what you should do, you should define a new speed, which is a velocity fluctuation, which is ui minus, you average over the speed of all these things, because you know already there is a net speed, subtract it from the individual speeds, so that will give you the velocity fluctuation. Now you calculate the correlation for these quantities, that will give you like, once you have removed the effect of the Q, how they are actually interacting with each other.
Okay. Yeah. Thank you.
So I guess if there are any further questions, we can have them over lunch. So for now, let's thank the speaker. Right, and so let's break for lunch. So we have an online talk at 2, so please be back in time for that.